Hi, it's Phil Dooley here in the west wing of the jet building, talking to Robin Stafford Allen. Hello, Robin.
Good morning, Phil. Hi.
So, tell me about the west wing.
Right, the west wing is where we do the cryogenics for the jet machine.
Okay, and you work in this area?
No, I presently work as a mechanical engineer in the ITER group, but I used to work in this area and I have a strong interest in cryogenics.
Okay, and is that related to our little demo today?
It is. We're going to do an experiment demonstrating superconductivity, which occurs at low temperatures.
So, this is our superconductor then?
We've got some superconductor here, yes. The little black blobs are high temperature superconducting material.
Right.
Which will exhibit superconductivity above the temperature of liquid nitrogen.
So what actually is a superconductor?
A superconductor is a material that as you cool it down, it exhibits two effects. The first one is, as you get it cold, the electrical resistance drops until suddenly it disappears to zero. And that's the critical temperature. That's when superconductivity starts.
Yeah.
Absolutely no resistance to the flow of electricity. The second effect is an effect on magnetic field, and we're going to show here that we get a strange effect with magnets.
Right.
In this demo.
Okay.
So we need to cool it down. So
Right.
I'm going to cool it down and then we'll get on with the demonstration. By adding liquid nitrogen to this dish. There we go, we're cooling down. I'll hold that while you put the magnet on. That's it. We're nearly there.
There we go. It's just hovering there by itself.
So we have it now levitating above the superconductor because of the rejection of the magnetic lines from the magnet itself, and it will levitate.
So basically the superconductors making currents become an electromagnet in a way that...
The surface is, yes, just the surface. Just to prove there's no trickery, here's the magnet on top of the superconductor when it's above critical temperature, and it doesn't attract or repel at all. We can try it with the small magnet.
Let's try the small one.
Let's try the small magnet. Oh, that's good, yes. And there's the small magnet, as you can see, floating above the central bit of superconductor. And it's free to spin.
Amazing. Not touching at all. So how will this be useful in ITER?
Okay, Phil, we're not going to use this magnetic effect. We're going to use the low resistance effect of superconductors.
Right.
That means that we will have no electrical resistance in the coils as we pass current of tens of thousands of amps through these coils. The big difference between jet and ITER is the fact jet only has copper coils, where we can limit it with the amount of current you can pass through the copper bars.
Right.
In ITER, big superconducting coils for the toroidal field coils and the poloidal field coils. They will all be low temperature superconductors.
So that will make quite a large magnetic field then?
It'll make a strong magnetic field for confining the plasma well, but you have to keep them very cold. You have to keep them around 4 degrees Kelvin.
Right.
That means liquid helium rather than liquid nitrogen.
But overall a much better system.
Overall it means we can have a bigger machine with a higher magnetic field, better confinement for the plasma. And that's the whole point of the superconducting side of ITER.
Right. Well, I better let you get back to designing it then.
I'd better get back to my desk job.
Thanks for your time
Good to
today.
see you, Phil. Cheers.